Hello and welcome back to Gaming Like It's 1979. Today we're going to continue on our adventure with the game Turing Complete. So we had done a lot of these levels and there have been several updates to the game. It's still not really reached its 1.0 release. So I did go back and do some of the earlier levels. I'm not going to update the videos. There are a few significant changes, but more or less the same topics have been covered. So where are we? Well, the last thing we did in our third video was unlock the component factory, which has us now about to get to building actually in the CPU architecture section of the game. So I want to start off by saying how much I love Turing Complete. This game, I mean, I play a lot of these games. If you've looked at this channel, you know there are innumerable games based on the NAND to Tetris class. And this is, yes, another one. But there has been so much thought put into not only the UI of the game, which is extremely polished compared to many of the others, but into the level design. There's some thoughtful things here. As someone who has done the NAND to Tetris course and in fact taught it, there are things in here that I find challenging and I really like them. And that's why, more than anything else, I'm spending so many videos going through this game. I'm not trying to rush through it. I'm not trying to do the fastest Let's Play. I'm really trying to enjoy these levels, and I hope it works for you too. The game. So let's take a look here at registers. And they're telling us that we are going to build a Turing Complete machine, a true computer in every way. So they're criticizing my layout. It's a fair cop. And they're locking some of the components in place. The mess you make is saved between levels. That makes me a little anxious, if I'm honest. Okay, we need to create a circuit which can copy from a source to a destination. The instruction byte up here determines the source and destination. Bits 1, 2, and 3 give the destination. We can play with those. And bits 4, 5, and 6 give the source. So it looks like our opcode there is destination, comma, source. They can be one of 6 registers named 0 through 5. Off by 1 errors or so. So much fun. And there's a dedicated input component, which can be the source, and an output component, which can be the destination. And then they're telling us what the bit patterns are. So all on is unused. And that is probably also true for the outputs. Okay, click the instruction icon in the upper corner. Upper left corner. Is there instructions? I don't think they mean that icon. Oh, they do. Look at that. So that would be, for example, copy input to output. This is copy register 5 to register 1. Okay. Well, that's nice. So what have we got here? Let's see. Everything's locked in place. We got lots of space to work from. So up here is our instruction in the upper left. This is our dedicated input and output. Our input, which has an input connection and an enable-disable bit. And similarly for the output. Okay. So right off the bat, even though this is called input, it is not the case, unlike in many of our previous levels, it's not the case that the input always comes from here. The input is going to be determined by the instruction, and it could be one of these registers here. So whatever we do, a lot of logic is going to be built around this instruction here, right? And what kind of logic are we going to need is going to be a lot of, I think, switching and muxing and perhaps demuxing. We've got a counter, we've got a register, we've got a mux, we've got a switch. And everything coming out of these registers is 8-bit. And going into these registers, there's the load and save value. So this is a bit tricky, because what we want in the end is some wire somewhere over here. Is it going to do random every time? Some wire somewhere over here, which is going to be carrying the value from one of these 6 registers or the input. And then that wire is going to need to be fed back into both the output and all of these registers as the input, right? I think that's true no matter what. And then the actual control logic is going to be about enabling this save bit to, or the enable bit on the output to decide whether to write that value. Working backwards, that means that the load bit on all of these registers and the enable bit on the input is going to be enabled for the one value, which is the source. All right, so I still don't quite know how this is going to look, but let's start doing some color coding. Let's see, we don't want to use colorblind bad colors. Let's say that purple is our inputs, our input bus, kind of, with the 8-bit values, and blue will be, this dark blue will be our output. So what I'm going to do is load means, no. Load is for going out in this case. I always get confused by the load and save and the inversion in the meaning of load and save in assembly language and in computer architecture. Save means a value going into the register. Load means a value coming out of the register. In fact, we can see that. Can I toggle these things? Will it let me? It will not let me. Damn it. All right. Well, what I want to do is let's work on the input side. So we're going to put some purple wires all through here. These are the things that need to be enabled based on the source destination, the source part of this bit, right? And that's true there. Okay. And let's go ahead. We know that whatever we're going to do here, this is going to have to get broken out. Let's use a different color for that. And we know that bits 1, 2, and 3, I believe they said, are the source. Let me double check that. Yes. Nope. Bits 1, 2, and 3 give the destination. 4, 5, and 6 give the source. Okay. So 1, 2, 3, 4, 5, and 6. Right? So we don't know what all these things are going to be hooked up to, but we do know that one of them is going to be active. Likewise, then, if we have done our job correctly, can I have another purple? Let's use this off red for the data bus. If we've done our job correctly, then only one of these will be active, right? and we should be able to connect all of these together in one big bus. And ideally, only one value will be coming out of there. That's my belief. I don't know if that's true. You know what? Let's test it. Let's wire up an on bit to, you know what? We'll wire it up to the, we'll wire it up right here to the input. And let's make sure that what I just said is true. So obviously this isn't going to pass the test, but all I want to see is that 63 is on this wire, right? The input from here is on this wire, and we're not seeing the disturbing, there's a problem. Now, if we were to wire another on bit to here, I would expect to see some sort of error here. Yes, good, short circuit. All right, so that's our assumption, is that we're going to somehow make sure that only one of those purple wires, the darker purple, goes on. So let's do the same thing now with our load bits. So our save bit, rather. So save means that it's being written out, essentially. So we're going to draw some dark blues. Ooh, that blue is hard to see, isn't it? Well, I hope you can see it. I'm going to use it anyway. All right. And so the save bus is the value going into these. So let's use a nice bright cyan. And that's going to be going to here, and that's locked in place, so we can't move it. And we'll do a little jog there and run that up here. Okay. And then we will fire that into there. Now, logically, we know that nothing gets onto that save wire, but that it came in through our input bus somehow. So actually, I don't need this jog here. I think I can actually join that up and join that up there. I'm going to leave it a different color just to be really clear that that's a value that's being saved. So these are all off. Let's do our little test again with those. And what I expect to see is I expect to see the value come into here, go into the blue wire, and be written out to there. And I expect no short circuits. And that looks correct. Okay. So I think that is actually the entire data bus for what we've done here. And the corollary there is that at this point, I should never, you know, famous last words, but I should never need to touch another 8-bit wire. So I think I want to do this as well. This is the destination, right? Logically, it makes sense to me to work on the source part of this first. I've already forgotten. Bits 4, 5, and 6 give the source. Okay, so that's our purple. Right. And that's what's going into our load. So how do we write a smile? This doesn't feel like it's impossible. It's just 4, 5, and 6. So all zeros is reg 0. That's register 1. That's register 2, register 3, register 4, register 5, and the input. I feel like in a just world, we would have already made this component, and I think We kind of did. I think we made a component earlier that was very early on. I'm going to go back to the level map here, in fact. Odd number of signals, counting signals. It's over here somewhere. 3-bit decoder. This was in fact, right? So what this does is, given these inputs and outputs, this is in fact, is this the inverse of what we want? Activate one of these bits. So this converts that 3-bit input into 1 bit per wire, essentially, right? So we can actually, this really looks ugly, I have to say. This is not the best design, but we can take what we've done here, 1, 2, 3, 4, 5, 6, looks like with 8 3-way AND gates and some judicious use of NOT gates to basically replicate that bit pattern. And we can make a 3-bit decoder, and we can then use 2 of those to simplify this logic. I think that is the right way to do this. I like that idea. So to do that, this is the first time I've actually done this. We're actually going to use this component factory. And I certainly hope that I could use my, yes, so there's my ALU. So that's there. We can use these custom components. All right, we're going to go to the component factory. We're going to make a new schematic. 3-bit decoder. All right. I'm kind of surprised that I can't actually use the 3-bit decoder that I already made. Can I? Maybe it's there? No, I don't see it. Probe, twist, output, input. No, we're going to have to actually do it. Oh, wait. I lied. Look at that. We don't actually need to do it. It's in the 1-bit category, which was not what I expected. All right. Well, so much for that. Let's go and switch back to our ALU here and then delete the thing we just made, or the thing we were about to make that we didn't. All right. So after all that, it turns out we already have the part that we need, which is this 3-bit decoder. So this, how do I do this so I have enough room? There's a disable. I don't think we need the disable input at all. So we'll go ahead and pull that over there. Eep. You can right-click on these little nodules to get rid of them, which is nice. And we'll put another one right here. Oops, and we want to change the color of that circuit, don't we? 2, 3. Okay, so now at this point, I think I could literally just pull these puppies out. Let's go ahead and try and make it a little neater, I guess. I don't know if it's going to work or not. We'll try it. Put it roughly there. All right. So that's our 1. I try and do right angles when I can. Honestly, the games, the way it works, the way it routes these wires, it almost punishes you for doing that. 3, 4. I find myself with a gaping mouth sometimes when I concentrate. I'm sorry if it looks super ridiculous. Very self-conscious about it now. Okay. And our 8th bit is going to be unused. And this is just going to go around here. Right. Okay, so that's our load bus. And the save bus, it's going to look a little silly. Can I rotate this? I think I can. If I recall correctly. Undo, undo. If I recall correctly, if I select it, I can move it over here. Yep, and immediately they all get ugly. Can I? There we go. Ooh, that's hard to look at. Okay, try this again. I change my color so I can keep track of what's what. And bring that there. Okay, so now we want to do the same thing, but with our blue wires. One. The one going to the output is going to be kind of weird, sadly. That's okay. There are no prizes for being neat here. Although, no, it's fine because they've locked the, as long as I'm inside the lines, I think that's the key here, is that if my wires are outside of the bounding box drawn by the components, that could be a problem. But as long as all the wires are inside, I think it's okay. Okay, one more, and then the one to the output. So if this actually works, I'm going to feel very smug, and the reason I'll feel smug is that I will not have actually... I feel like I haven't done any real logic here. I've just kind of done it a step at a time, but I don't know that it's going to work. Let's do a single step and see if it works. That looks like it's doing it. We solved the level. I feel extremely smug because at no point did I have the entire design of this in my head. I just literally kind of tried to break it down to its smallest components. Which is sort of the opposite of what you want to do. All right, which of these we got left? We have instruction decoder, and we have conditions. I don't know which of these to do first. I guess instruction decoder is a bit lower on the tree, so let's do that one. The circuit we built can copy values between registers, while the arithmetic engine can do different operations on 2 inputs, but we need to be able to do both in the same circuit. Build a decoder which will decide which mode our computer is in based on the 2 bits we haven't used yet. Oh God. To distinguish between the instructions of 4 different kinds, the 2 highest bits, immediate, calculate, copy, or condition. Okay. And what are these outputs? The outputs... I mean, this is basically a 2-bit decoder problem, right? That's all it is. And we're getting... I think I could just use the 3-bit decoder and ignore the high bits for this. And in fact, I am gonna do that. This is not like... This would upset some people because it is not efficient, right? Like, I'm probably using more AND gates or NAND gates than is necessary to actually accomplish this. But I don't care. I don't care about efficiency, right? And then 1. I actually did not look and make sure. Let me see. So we've got immediate, calculation, copy, and condition, and immediate, calculate, copy, yes, so those are in fact in order. That's great. Okay, and one more condition. I think that'll do it. It's got to work. Let's see. Actually, we can test this, can't we? So immediate, calculate, condition, and copy. And then anything else is ignored. think that should work. Okay, so it doesn't like that. Why doesn't it like that? It says it's a... Oh! Because I'm a dope, that's why. Because I wired this. There's probably someone watching this YouTube video who is screaming this the entire time. I wired this to bits 1 and 2. But in fact, oh, my beautiful lines all ruined. In fact, it needs to be wired to the highest bits. And I'm not going to make those lines neat. Great. Circuit has been saved to the component factory. Okay, great. Time to merge in the arithmetic engine circuit you made previously with the register circuit. The calculation circuit was saved in the component factory and can now be added as a component. If you forget what each pin does, check the circuit. Use the decoder you built to figure out if we should copy between registers or do calculations. For this level, we only have to worry about the copy and calculate mode. When in calculate mode, so that's this one, take reg 1 and 2 as inputs and save the result in reg 3. Tip, don't forget the 3-bit decoder component has a disable bit. Oh, okay. Yeah, I'm having trouble envisioning this. For this level, an extra pin has been added to the registers. This pin always is very complicated. I'm worried about this because they're breaking all of these rules and kind of like adding things parenthetically, which makes me feel like this is a level that a lot of people had trouble with and they kept tweaking it. I don't know. Always omits the value of the register. Oh, God. All right, so let's look at this. Okay, we have these two wires up here, right, which are not used. We know we're going to have to use them. That's interesting. Okay, so makes perfect sense, actually. It's using the whole value. So we're going to go and we'll make it gray because it was gray here. All right. Okay. Let's just step through this a little bit. Yes, the decoder is working. It's changing the value. That's great. Okay. Copy input 123 to reg 0. That worked. That is what? That's a calculation. Copy input 123 to reg 0. What I want to see here is, oh, damn it, I can't actually go past. Here's what I'm thinking. Here's why I'm struggling. My belief is that what we've already built here, all of this, essentially already implements copy mode. That's what I think. So can I change the instruction? Let's see. Destination is... Oh, something is... What was that? Why is that breaking all of a sudden? Oh, because it's 0 to 0. Right, we don't want that. And that's an invalid. All right, so now... Oh, because I was doing the wrong... definitely feel like I'm not understanding something here. Because this was not doing that. No, it's an extra pin, so it should still be working. So why isn't it? Load output, always output. Did adding that pin somehow ruin this? Should it have not worked on the previous level at all? Should I have been getting this error? I don't think so. Right, so our instruction, let's do our instruction. Copy. Copy is the highest. There we go. Okay. That should be copy reg 2 to reg 1. Copy input to reg 4, right? So let's turn everything off here. Copy input to register 4. Register 4 is that one. The load bit is high, or the save bit rather is high. And 2 is going in there. I think that's correct. Okay, so as long as so it's copying from register to register is what seems to trigger that. Register 2. Very confusing. That's register 4, and that's okay. And we can see that all of these are in fact disabled except for register 2, which should be correct. That's disabled. And that's disabled. Yeah. Based on the fact that this first value works, I'm going to choose to not worry about this for now. We'll see. Maybe I'm wrong. We'll find out. All right, so what do we need to do when this is not set to calculate, but it's set to an instruction of some sort, right? A valid instruction, say OR. Which is that. Well, in order to do those instructions, we're going to need an ALU. And here is our ALU. Oh, it's so cute. It's so cute and little. It has 3 inputs and an output, and those inputs are not very labeled, are they? Can I label them? Gonna go back to the level map here. Arithmetic engine. They're not labeled here either. They're just input, input, input. The first input is the instruction. Input, input. Okay. Is it labeled as an instruction there? That sucks. That sucks that that is not labeling that as instruction. I wonder if It's because I 8-bit input. Label direction, okay. Label text. I'm going to put instruction there. Okay. I'm going to call this input X, and I'm going to call this input Y. I don't know that these labels are actually going to show up, but we're going to try. Okay. Do I have to do anything to save this? I don't think so. Wrong level. Go back here, and I'm going. Oh, look at that. Okay, now we have actual labels here. So, whew, much better. Okay, so if this is that's calculate. I think it's the second one. It's that. No, I'm on the wrong. Right. It's this wire. If this wire is true, let's make that white. If that wire is true, then our ALU does some work. And our ALU gets the instruction. And the instruction, going back to the arithmetic engine, is just a code, and it has lots of undefined stuff. We don't have to worry about that because we didn't make any of it. So the instruction is literally just this. Just this. Okay. And then we've got where does they told us it's, I think, read from registers 1 and 2 and write in 3. Calculate, add register 1 and register 2 and store the value in register 3. All right, so that's why we have these emit things here. This is so that we don't have to mess with the addressing or the enabling. This is basically ignoring the load. Let's use orange because this is so special. That's register 0. We want register 1. I think it doesn't matter. Actually, it does matter because these are ordered because there is subtraction. So I think 1 has to go here. And 2 has to go here. Okay. And so then we have an ALU output, and then output has to go to register 3. Now this is tricky though, right? Because right. That's why they made a point of telling us that the 3-bit decoder has a disable bit. And so what we're going to do is when this is on, we're almost surely going to have to change this. When this is on, we want to disable that. And I think we will also, for safety's sake, want to disable that too, if we're not in copy mode, basically. So I'm saying that we're going to have to change this. I mean in subsequent levels. For right now, I'm literally wiring it's an instruction to disable those two load things. All right. And then in this case, the other thing we're going to want to do... Ooh, is this right? I don't know if this is right. No, that's not right. How do we enable the saving of this? I think we need a mux here for this one. I don't think there's any way around it. Mux or a switch of some sort. Unfortunately, our muxes are 8-bit muxes as given. I might have to make my own mux, a custom 1-bit mux. No, I could just OR these together, can't I? Because this will always be low. Yeah. I can just use a 1-bit OR, I think. Getting messy. Okay, so blue is going to go here. White is going to go there. And then we'll call it white again because it's kind of a control bit. Okay. Still not working, but that's okay. Oh, because the output is just doing nothing. All right, so this is nice because we see that the correct value is in fact coming out of the ALU. That's what we wanted. So we need to figure out how to get that value down to our bus. But if the decoder is disabled, then that bus should be totally dead. I think we can do that. Short circuit. Poop. Okay, why is that short circuit? It's a short circuit because this is enabled. Oh, because it's actually this. Yeah, okay, fine. What's the right way to do this? Did I just... No. So what I want to do is I want to get a value onto here, right? What is this value coming out of here in the copy case? Let's make sure it's 0. It is 0. Can I do something like... I think I could do something very similar to what I did with the OR here. It's certainly not great, but I think I can do this. Okay, we're going to make it blue. We're going to add. This is so inefficient, like somewhere an architecture person is screaming at me. Okay, we're going to do that. And then that is the value. That is going to go into there. Whew, that's ugly. That looks like it's working. Ah. All right, what did we break? Copy register 0 to register 3. Register 3 should have value 4. All right, so we actually have a non-zero value coming out of the ALU here. And that is definitely wrong. So my assumption that the ALU would always get a zero value when we were in copy mode was false. Makes sense. There's nothing here saying that it should be in copy mode, right? And the ALU does not have a disable bit. So I think our clever haha add solution was wrong. But we could, by the same token, this is kind of dumb, we could just use an 8-bit mux, I think, to take a value based on, yeah, that's a more correct solution. All right, so we'll put that there, and we'll put the blue one as our first input, the orange one as our second input, and then the bit here is actually, again, this white bit. That was much more correct than adding these values. All right, and that's working. Wow. Well, that is our calculations level. Next, we got program and conditions. Oh my God. So now the game is really throwing us a curveball, because everything we've been doing with circuits up until now is kind of going to go away or be obscured at another level of abstraction. So the instruction input component has been removed. It has been replaced by a program component. Every tick, use the counter to load the next instruction from the program's memory. You must use the counter component. That makes perfect sense. All right. So we're going to grab our counter. Where is it? Is it right in front of me and I'm just not seeing it? I see an add component. Delay line. I don't see the counter. Oh wait, 8-bit counter right there. All right, replace the input code with the program component. Oh, I see. So this is actually our whole big component with some numbers. And so at a base level, that's what they want. But we need a program counter, right? We need this to advance. So how does this advance? How do I make this advance? Oh, it has input, address. Address as an input. Presumably, if address is 0, right? Overwrite value, increment versus overwrite. We're not doing conditionals yet, so we don't have to do that. So we can literally just wire these up. And I think that'll do it. I think that's it. Yep. We now have a computer that will march through memory from the beginning to the end and feed those values into the rest of our computer. All right, I think this is the last level I'm going to do today. We are going to look at immediate values. We need a way to directly move numbers from our program into registers. We use the immediate mode when the two highest bits are both off. Right. When in immediate mode, the whole byte is interpreted as a number that we save into register 0. This means we can save any value. Okay, so level input is coming from there. So in this world, it's 0. Add constant loading. So this is an example of immediate mode, right? And that's this control right here. So I think we want to disable, we want this white line to go high when we're in immediate or calculation mode. So in both these cases. So let's go ahead and do that. Okay, and we will pull these down here. All right, so that in that world, if we're in immediate or calculation mode, the only effect here no, because this OR is going to enable this register. So that's a problem. That's a problem. All right, let's go and undo all that. Okay. So we need a slightly different story here. I think this OR is okay. And this mux is also okay. But the things going to our decoders need to be separated out. So let's pull that up there. Get rid of that. Get rid of that. Oops. Okay. And that. Boy, that's ugly. Oh, I see. It has to do that. That'll go to there. Right. So now we've separated that. And now we want our OR back. Right here. This is one of the inputs to that OR. And then this is the other input. So let's, I think we can also keep this as white because I think it's going to be relevant. However, this one, let's make it a, we're running out of colors here. Well, keep it as gray. All right, so now that will be disabled in that case. And this one will be disabled in that case. However, we also then need to do a similar thing that we did here. This is register 0, I said, right? That'll go here. And we only want it from here. Oof. Man, that's ugly. And then that becomes yeah, I like the idea of using white as a special case because it stands out a little bit. It's our control logic. I would probably use red, honestly, if I was doing it just for myself, but I know that a lot of people are red-green colorblind, and I want to be accessible. And immediately not working. All right, so that's good. Let's look at this case. Immediate 63 to red 0 to register 0. Oh, right, because the value in this case is this 63. So similar to this, we also need an 8-bit mux. And put it right here. This can go away. This is going to be our default value. That'll go there. Using gray was a mistake. Oh well. This is our instruction input. So that's our selected value. Try that again. Okay, and then this right here is also what triggers the selector. Good. All right, but we broke some cases. What do we break? Copy the input to register 0. So something in our logic. Right, and what we can see here is that the wrong value is coming out of the mux. Why is the wrong value coming out of the mux? Because we're using this save enable flag, which was not what we wanted. We actually want to use this. 2 wires both using white. That was my problem. All right, try it again. Looking good. Great, and that's our immediate values. Well, we are very close to having a working computer here. I'm tempted to push on, but I know that this video has gone very long, and I also don't want to, as I said, I love this game, and I don't want to ruin it for myself by turning it into a job. So next week, or next session, we will be doing this conditionals, and we will get at least finish the working computer part of Turing Complete. This has been Gaming Like It's 1979. Thanks for watching.